Hello! The first topic this week is about homogeneous second-order linear differential equations with constant coefficients. So it's a very specific type of second-order ODEs. So let's start to see what it means. We look at second-order ODEs. There are any ODE that takes up to the second order of the function we're looking for. So we have y appearing, we have y prime appearing, and we have y second appearing in our definition of the ODE. We usually not like to rewrite it as y second equals a function of time and y prime in a very similar way as we did for first order ODEs. And now we want also to impose to our ODE for it to be linear. That means that no terms that have both y prime and y can appear on the right hand side. So we have a term that has only the time that we call g, a term that has y prime multiplied by a function of time, and a last term that is y multiplied by something that is a function of time only. We usually like to rewrite it as y second plus function of time y prime plus function of times y equals function of time. Why do we like formulating it like this way? It's mainly historic reasons. It's just nicer to look at it in this way because in this way we can put aside the term g, and we'll see later how this term is particular on its own. Sometimes we rewrite it as a function of time multiplied by y second as well. Obviously, these two things are related very closely because when this capital P is different than 0, then we can divide everything by capital P, and we have a relationship between these two rewritings. But we're mainly going to be looking at the situation in which y second doesn't have any coefficient other than 1 in front of it. If it has, then when pt is different than 0, then we can divide everything by pt and retrieve what we have before. So we would have small pt equals capital Q divided by capital P, small q is equal capital R divided by P, and small g is equal to capital G divided by P. That's why we need pt to be different than 0 for this to happen, because we're dividing by P all the time. When we're looking at second order ODEs, we also need initial conditions. In first order ODEs, we used to need only one initial condition. Well, second order ODEs require two initial conditions. What you want to think about is, ideally, how many times do you need to integrate your derivatives in order to retrieve the solution? And for second order ODEs, you need to integrate twice. That's not how you actually solve second order ODEs, but this is the idea behind. And since you're integrating twice, you have two constants that pop up. And in order to fix two constants, you need two initial conditions. We say that a function is homogeneous if the term that is not multiplied by any y or any of its derivatives is equal to 0 for all times. So if our small g of the previous slide or the capital G of the previous slide is equal to 0 for all t's, then we're talking about homogeneous ODEs. The opposite of homogeneous is called non-homogeneous. So this term g is called a non-homogeneous term or forcing term. The idea of calling it forcing term is because in physical systems, it does represent the external force that is coming into the system. So we are starting this week by looking at a very neat subset of all second order ODEs. We're looking at linear second order ODEs, we're looking at homogeneous second order ODEs, and we're also requesting it to be constant coefficient. So with all these impositions, what we're actually looking at is an equation of the form a y second plus b y prime plus cy equal to 0, where a, b, and c are some given constants. Let's look at an example and see if we can start solving something simple in this form. For example, we can look at y second minus y equal to 0. We can write it like this, or we can write it as y second equals to y. So taking two derivatives gets you back to the initial equation, the initial function. We're also imposing two initial conditions. We want at 0 the function itself to be equal to 2, and at 0 at the same time the derivative of the function to be equal to minus 1. So what solves y second equals to y? The first thing we can think of is that a solution is the exponential of time. We know that taking derivative of the exponential gives you back the exponential, so the second derivative of the exponential is itself. But also the exponential of minus t, the second derivative gets you back to have no coefficient in front. So also exponential of minus t is a solution. So we are in a situation in which we have two solutions for our ODE. We are not looking at initial conditions yet. So let's wait a second to look into that. We're just looking at what solves y second equals to y. And we retrieve two functions, different functions that satisfy that. But there is more. If we multiply either of these functions by a coefficient, let's say 5 exponential of time, that also satisfies our equation. Or 7 exponential of minus time, that also satisfies our equation. There is more. Any sum of y1 and y2 also satisfies our equation. Actually, to be in complete generality, anything that has the form constant times exponential of t plus other constant exponential of minus t is a solution of y second equals to y for any value of the two constants we have chosen. Let's check this statement. So we introduce y equals to c1 exponential of t plus c2 exponential of minus t. And we check that the second derivative is equal to y. So we take the first derivative, and the first derivative is c1 exponential of time minus c2 exponential of minus time. Then we take another derivative, and the sign in front of c2 changes again. So we are back at y. So y second is equal to y for any value of c1 and c2 that we can pick. And now we ask ourselves, can we fit it in the initial conditions? So we have a solution that depends on two parameters, two choices of c1 and c2. Can we choose these c1s and c2s in such a way that it fits the initial conditions? We have two constants that we can choose. We have two initial conditions. Can we match them in some ways? And in this case, we can. So we know that y has to be 0. It has to be 2 at 0. So we want that our y computed at 0 would be equal to 2. So c1 exponential of 0 plus c2 exponential of minus 0 is equal to 2. That gives us that c1 and c2 plus c2 are equal to 2. We also want that y prime at 0 is equal to 1. So we have c1 exponential of 0 minus c2 exponential of minus 0 is equal to 1. And this gives us two equations to solve. We want c1 plus c2 is equal to 2, and c1 minus c2 is equal to 1. And we can solve these two equations at the same time, and we have a unique solution. That is, c1 is equal to 1/2, and c2 is equal to 3/2. So our solution to our ODE, including initial conditions, is this equation, is this function, 1/2 exponential of time plus 3/2 exponential of minus time. In general, how can we solve a homogeneous, linear, second-order ODE with constant coefficients? We do it like this. We assume that the solution is an exponential. So we assume the solution has a form exponential of a coefficient r that we don't know times time. So we take the derivatives of this exponential of rt. Every derivative just sprouts a constant r in front of the function. So if we plug this in the ODE that we're looking at, we retrieve that we want AR squared times U plus BR times U plus C times U is equal to 0. And U is an exponential, so U is never 0, so we can cancel it out and retrieve a function, an equation, AR squared plus BR plus C equals to 0, where A, B, and C are known from the problem, while R is the unknown that we were looking for. So now we can solve this equation. This equation is very important, and we're gonna loop back at it multiple times. It's called the characteristic equation. And if we can solve it, and we can find two values of R that solve the characteristic equation that we will call R1 and R2, then we're good. If they are different, so R1 is different than R2, then the solution is in the form that we just saw. It's C1 exponential of R1t plus C2 exponential of R2t. This week we'll also be looking at the situation in which R1 is different than R2, but it's not real. So here we're looking mainly at R1 and R2 being real. Check as a homework that this equation does satisfy the ODE that we started with. Now that we have a solution that depends on C1 and C2 times some exponentials of things that we know, then we want to find the C1s and the C2s, and we use the initial conditions to do that. So as general initial conditions, we have that at t0, some value of time, we have a fixed value of the function we're looking for, y naught, and a fixed value of the derivative of the function, y naught prime. So we need our solution to fit these requests. That means that C1 exponential of R1 t naught plus C2 exponential of R2 t naught is equal to y naught, and C1 R1 exponential of R1 t naught plus C2 R2 exponential of R2 t naught is equal to y naught prime. They're very similar equations. In the second one, we're just taking the derivative, so we have these coefficients R1 and R2 popping up. Notice that y naught and y naught prime are known, exponential of RT t naught are also known, and R1 and R2 are known. So the only unknowns in this two equations are C1 and C2. And then it's two equations in two variables. We can solve it. Let's go for an example. We have y second plus 5y prime plus 3y equals to 0, and we want both y and y prime at 0 to be equal to 1. So we assume a form of the solution to be ut equals exponential of rt. That allows us to write the characteristic equation, that is r2 exponential of rt plus 5r exponential of rt plus 3 exponential of rt. We get rid of the exponential of rt's, and we have the characteristic equation being r squared plus 5r plus 3 equal to 0. Second order algebraic equation. We can solve it. We have a solution that r1 and r2 are minus 5 plus or minus square root of 13 divided by 2. That means that the solution to our ODE is C1 exponential of R1t, that is exponential of minus 5 minus square root of 13 divided by 2 multiplied by t, plus the other part of the solution is C2 exponential of minus 5 plus square root of 13 divided by 2 multiplied by t. We then need to fix these C1s and C2s. So we want that C1 exponential of 0 plus C2 exponential of 0 is equal to 1, and C1 R1 exponential of 0 plus C2 R2 exponential of 0 is equal to 1. So we have, this simplifies to C1 plus C2 is equal to 1, and minus 5 minus square root of 13 divided by 2 C1 plus minus 5 plus square root of 13 divided by 2 multiplied by C2 is equal to 1. We can solve this. C1s and C2s are ugly. They have square roots all over the place, square roots of 13 that are not particularly nice, but we can solve it and we can write explicitly the solution for y. So y is C1 exponential of R1t plus C2 exponential of R2t. That in this case have this format with the various square roots and fractions.